podcast, we'll limit to elegant simplicity, Pascal's triangle, and binomial theorem. Please mark out pages 529 to 540. All right, let's take a look at the next page. Okay, now we're looking at 3, modeling with polynomial functions and data. The teacher works 1, the student works 2 and 3. Warm up. Use technology to determine the linear regression equation for this each set of data. Go ahead and underline that. It says linear regression. It's telling you which regression to use. Okay, so let's go ahead and do number 1 using Desmos. So I go to graphing calculator, add table, and so I'm going to add the points. So 3, 4, 7, 6, -2, -4. Zoom out just a little bit to see the points. And then I'm going to click on these dots right here. Linear regression. I'm going to round to 1 decimal place. So that's y equals 1.1 x minus 1.0. Okay, go ahead and finish up number 1 and then answer 2 and 3 on your own. And let's take a look at the next page. Getting started. Release your regression. Recall that regression equation is a function that models the relationship between 2 variables in a scatter plot. The regression equation can be used to make predictions about future events. Any degree polynomial can model a scatter plot, but data generally has one curve that best fits the data. You may also recall that the coefficient of determination r squared measures the strength of the relationship between the original data and the regression equation. The values range from 0 to 1, with the value of 1 indicating a perfect fit between the regression equation and the original data. All right, go ahead and mark out the rest of the page. All right, let's take a look at the next page. 3.1, applying a polynomial regression. City planners consider building a new stadium on several acres of land, close to the downtown of a large city. They monitor the number of vehicles entering and exiting downtown from a major highway between 1 p.m. and 7 p.m. to determine the current traffic conditions. 1. Analyze the table of values that represents the average number of vehicles entering and exiting downtown during the given hours of a typical weekday. The values from time represent the start time for the full hour over which the vehicles were monitored. Let's take a look at A. Describe any pattern you notice. Explain the patterns in the context of this problem situation. The number of vehicles increased to reach a maximum at 5 p.m. and then decrease again. This is because rush hour occurs around 5 p.m. B. Predict the type of polynomial that best models the data. Explain the reasoning. The data appears to be quadratic because it increases and then decreases. All right, let's take a look at the next page. Two, create a scatter plot of the data. Be sure to label your axis. All right, I've rewritten the table on this page so you don't have to keep flipping the pages back and forth. Let's go ahead and graph those points on the table. Okay, I've also labeled the scale from 1 to 7. This is time and hours. And I've also labeled the number of vehicles 1 to 24, and I've had to add a couple lines. Now remember, these are increments of 1,000. So this is the number of vehicles in thousands. So when we say 1 vehicle, we actually mean 1,000. Okay, let's go ahead and graph these points. So 1 p.m. 7. So 1, 7. 2, 10.8, which is almost at 11, but not quite there. 3, 14.5, which is between 14 and 15. And then 4 is 21.1, which is about right there, which is, and then 5 is 23.9, which is pretty much at 24. 6 is at 19. And then 7 is at 10. All right. Go ahead and finish graphing the points. 3. Use technology to determine the regression equation for the average number of vehicles entering and exiting downtown on a typical weekday. Sketch the regression equation on the coordinate plane in question 2. How well does the regression equation model the data? What is your prediction about the type of polynomial that best fits the data correct? Okay, so we're going to go in Desmos. Let's exit out our previous problem. Press the home screen. Now, before we graph, we need to adjust the window to match the paper. So we need to go from 0 to 7 and 0 to 24. Okay, so let's go ahead and do that. So adjust my window from 0 to 7 and 0 to 24. Okay, now I'm going to add the table. So 1, 2, and then 7, 10.8, 14.5, 21.1, 23.9, 19, and 10. And then we can zoom out just a little bit. All right, go ahead and finish that up. All right, so now we're going to do regression. And we're going to, linear doesn't work. Okay, let's try quadratic. Kind of works. And then now let's go to cubic. Cubic looks like it works the best. So we're going to go ahead and write down the equation. Okay, and we're going to round to 2 decimal places. So that's okay, so go ahead and write that down. And that's with a coefficient And then let's go back and sketch the regression, which we know comes up, back down, up, and back down like so. All right, so go ahead and finish up the graph. Make sure you have the equation written down. All right, let's take a look at the next page. 4. Use a regression equation that best models the data to make a prediction. Downtown is congested when more than 20,000 vehicles are on the streets and highway. Predict when the downtown will be congested. Explain your reasoning. So to do that, we're going to graph y equals 20. So come down here. I graph y equals 20. And I'm looking at here and here. Let's go ahead and round these times to whole numbers. So let's go and round that to 4 and 6, since we're talking about hours. So downtown will congested between 4 p.m. and 6 p.m. Okay, go ahead and finish up A. B. Predict the hours when the number of vehicles that enter and exit downtown is less than 10,000. Explain your reasoning. Graph y equals 10. Okay, so I'm going to come over here. I'm going to change the y equals 20 to y equals 10. And let's go ahead and round those to whole numbers. So that would be 2 and 7. So fewer than 10,000 vehicles are on the highway between 2 p.m. and 7 p.m. All right, go ahead and finish up B. Let's take a look at C. Predict the number of vehicles that enter or exit downtown during the hour starting at noon. So to do that, we're going to graph x equals 12. I'm sorry. X equals 0. All right, so remember, we're talking about thousands. So we need to multiply 8.44286 times 1,000 to find out how many cars were on the road. So let's go ahead and do that. Let's add another table, or Desmos. So I need to multiply 8.44286 times 1,000. And then let's round that to a whole number, so that's 8,443 vehicles were on the highway at noon. All right, go ahead and finish up C. All right, let's take a look at D. Predict the number of vehicles that enter or exit downtown during the hours starting at 9 p.m. Graph x equals 9. Okay, so let's go ahead and do that. Change the 0 to 9. I'm going to need to zoom out. All right, so again, we need to multiply negative 43.75 times 1,000. So let's go ahead and do that. So there were negative 43,750 cars on the highway at 9 p.m., which does not make sense because the number of cars cannot be negative. All right, go ahead and finish up D. And let's take a look at E. Predict the number of vehicles that enter or exit downtown during the hour starting at midnight the previous evening. So we need to graph x equals negative 12. Okay, and then I'm going to zoom out until I get to the intersection point. There. So then so I need to multiply 1,267.2 times 1,000 So the number of vehicles on the highway at this time were 1,267,200, which does not make sense in terms of this problem situation. Okay, go ahead and finish up E. Let's go ahead and take a look at the next page. Go ahead and mark out this page. And have a wonderful Wildcat day.